Next, we are going to discuss one of the most important topics, resonance. I am saying important because resonance questions have not yet been completely explored in the competitive examinations. Thevenin's theorem, maximum power transfer theorem, these have all been fully asked. They have been exploited in various exams. But resonance, still there is a lot to explore. Okay, so you can listen carefully here. What is the definition? Basic condition for resonance is what? The capacitive reactance is equal to the inductive reactance. Right? So this means that whatever energy the capacitor and inductor, they absorb energy for a half cycle and they deliver energy for other half. Right? Now what happens is when capacitive reactance and inductive reactance are equal, then for one half capacitive reactance will deliver the power to the inductor. In that half cycle the inductor will receive the power that is delivered by capacitance, and in the other half inductor will give the power to capacitor. So that means they will take no power from the actual source. What is the result of this? The reactive power will be 0. That means the reactance will not take any power, so that the real power P will be maximum possible. Okay. So this is the basis of reactance, right? Now let us see what about how the other parameters are going to be affected. So you can take this as point 1. Now when capacitive reactance is equal to inductive reactance, this means that the imaginary part of impedance is equal to 0, right? Because what is imaginary? Z is equal to R plus Jx. This is reactance, which is equal to XL minus XC. Okay. But if XL is equal to XC, then X will become 0. That means the imaginary part of Z will become 0. So XL is minus XC is equal to 0 under resonance condition. Similarly, this is impedance. What about admittance? Admittance is the inverse of impedance. This also will be 0, because what is Y? Y is nothing but 1 by Z, which you can write as R minus Jx divided by R square plus X square. Now if you keep X is equal to 0, then what will you get? Y, you are going to get 1 by R. Okay. So that means the imaginary part of Y is 0. Now Y we often express as G plus JB. What is this? This is the conductance and this is the susceptance, and we often write susceptance as BC minus BL. In the impedance, the inductive reactance is positive, whereas capacitive reactance is negative. In the susceptance case, capacitive susceptance will be positive, right? You can verify. 1 by j omega c is xc, so it will be minus j omega c, so that is negative. If you invert that, j omega c will be the susceptance, which is positive, and the inductive susceptance is going to be minus j by omega L. Okay, so that's why we are writing BC minus BL here, and for impedance you are writing as XL minus XC. Okay, so if imaginary part of the admittance is equal to 0, then BC minus BL will be equal to 0. So what is the other way to look at it? The impedance is purely resistive. So these are all various ways in which we can look at resonance. Okay. Now what about the relationship, the phase relationship between voltage and current if impedance is purely resistive? If Z is equal to only the resistance value, this means that you can write in terms of magnitude and phase as how? So you can write as mod Z angle 0 degrees. So what will happen to the phase relationship between voltage and current? This is equal to V by I is Z, right? So if this is equal to mod Z angle 0, then the angle of V is equal to the angle of I. The phase of voltage is equal to the phase of I. So that means voltage and current will be in phase under resonance condition. So if this is voltage, then I will also be having the same phase. What about the power factor? Power factor is nothing but the cos of the angle between, the phase difference between V and I. Okay, so that means phi is 0, cos 0 degrees, since phi is equal to 0 degrees. So this is simply equal to 1. So you have a unity power factor under resonance condition, right? Finally, if you talk about the power, like we already discussed, the capacitor and the inductor, they will alternate the power between themselves. So the power that will be delivered to the actual load will be maximum. Okay, power dissipated is maximum. Okay, now the power dissipated is dependent on the current. I square R is the power, right? So that means the current is also maximum. The current drawn by from the source, it is maximum. Now one important parameter in resonance is the resonant frequency. So what is the resonant frequency? If you remember the inductive reactance XL, you will write as J omega L. That means the reactance offered by an inductor of inductance L will be dependent on the frequency of the source as well, right? So we are talking about the AC sources here, and AC source will have some frequency time period. So that frequency will decide the reactance offered by that particular inductor, right? What about the capacitive reactance? This is minus J by omega C, or you can also write as 1 by J omega C. This is also frequency dependent. So if you plot this as the function of frequency omega, XL if you take, it is simply going to be a straight line, right, passing through 0, because XL is directly proportional to the frequency. What about capacitive reactance? This is inversely proportional to the frequency. So if you plot a graph, it will at 0 frequency, it will be infinity, XC will be infinity. So then it will rapidly come down like this. Okay. Now the point at which both of them are touching, what will be this point? This is the inductive reactance and this is the capacitive reactance, right? We are plotting both XC and XL here. So when both are equal, what does it mean? It is the resonant condition, and this frequency here is called as the resonant frequency. Okay. So that means the frequency at which inductive reactance XL is equal to XC is called the resonant frequency, or in other words, the frequency at which resonance occurs is called as the resonance frequency, and we denote it as omega R if it is angular frequency. Otherwise, we denote as FR. Omega R units is radian per second and FR frequency is in hertz. We can get an expression for this resonant frequency. How? By this condition, XL is equal to XC. This means what? Omega L is equal to 1 by omega C. So since this is the resonant frequency, we will take as omega R. So this implies that omega R is equal to 1 by root over LC. So this is the expression for resonant frequency in radian per second. That means the angular frequency expression. What about normal frequency? This is going to be omega by 2 pi, right? So 1 by 2 pi root LC will give you the frequency in hertz. You can see here that for frequencies which are less than the resonant frequency, the inductive reactance is lesser than the capacitive reactance. Whereas when frequency is greater than the resonant frequency, XL is greater than the XC, capacitive reactance. So one important point that you can write here is, for smaller frequencies, we say that the circuit is capacitive, since the capacitive reactance is dominant. And for larger frequencies, what will happen? We call the circuit to be inductive. One more interesting point that you can see is the plot of the impedance, the magnitude of impedance versus the frequency omega. Okay. So we know that at resonance Z we can write as R plus jx, meaning that what will be the magnitude? This is equal to root over R square plus x square. And you can also write in terms of the inductive and capacitive reactances as R square plus XL minus XC whole square. What will happen at resonance? XL is equal to XC. So mod Z is going to be the least possible value because this entire term will become 0. So at resonance, Z is equal to the minimum value. If the impedance plot is drawn for with respect to the frequency, you are going to get exactly like that. Okay. So there will be a point where ZL will drop to a minimum, and that will be the resonant frequency. Okay. So this is Z minimum. What will its value be then? Simply equal to the resistance R.